Today, our topic is transistor stabilization. So before going to transistor stabilizations, so I would like to discuss what is discussed in the previous session. So previous session, we talked about transistor biasing. So in biasing means we are adding voltages and maintain the collector current and VCE voltage at the output side is stable. We call it as biasing. So in biasing, we are seeing AC load line and DC load line. So what do you mean by AC load line? AC load line is nothing but we are giving AC signal to the input. We will calculate the quiescent point or Q point or operating point. That is called AC load line. Whereas DC load line means without giving any AC signal, we are calculating the operating point VCE, IC. We call it as DC load line. So DC load line can drawn from output characteristics, which is from VCC to IC, maximum saturation current IC. So that line we call it as DC load line. The intersection of DC load line and AC load line we call it as operating point or Q point or quiescent point. Okay, so this Q point may vary based on temperature parameters and physical variation of different transistors and some thermal runaway. So these are the concepts we seen in the previous class. Today's class I talked about transistor stabilization, how to stabilize the transistor amplifier without varying any parameters. For example, if temperatures is the main parameter, if temperature is increases means some of the parameters like base emitter voltage, amplification factor, and collector current, these are also changes. If changes means Q point is also changes. So Q point is also changes means so there is a instability problem will occur. So that type of problem can be reduced by using stabilization techniques. So in stabilization techniques, before going to that stabilization, how to choose an operating point in your DC load line. So we know that, so output characteristics, this is the VCE versus IC. We call it as output characteristics. It is a CE amplifier. So this line, we call it as, these lines are below 0 milliamperes. This is called cutoff region. This is called cutoff region. That means transistor is in off position. So both junctions are reverse bias. What about this region? This region we call it as saturation region. So saturation region means transistor is on position. Okay. So whenever VCE voltage is increases, linearly current, IC current, collector current is also increases. So that is called saturation region. So this is the flat region. So whenever VCE is increases, some point of time, this is the what do you call linear. Up to this point is linear, then it is the flat. So IB is IC is constant. So whenever IB is fixed, is equal to 0.1 milliamperes by varying VBE voltage and applying the or varying the VCE voltage, we will get IC is the linear from up to this point, then it is the flat region. Flat region is nothing but IC is constant. So this flat region we call it as So this flat region we call it as active region. This flat region we call it as active region. So in active region, transistor is used as a amplifier. Okay, this is the uh, application. So transistor is used as an amplifier. In which region means it is an active region, because first junction is forward bias and the second junction is reverse bias. So this is the different modes of transistor operations. So while coming to the operating point, so operating point is always fixed in the active region only. But how to fix this operating point in DC load line, or how to fix this operating point in active region? So for example, in this figure, so this is the active region, this is the load line, DC load line. So from VCC to IC. We know that what is VCC? VCC is equal to ICRC, ICRC. Here IC means VCC by RC. Okay. So how to fix the operating point means, so one criteria, if operating point is fixed to near to saturation region. So this is the P point. You can see this point is P. So if this point is phi, this P is nearer to this is the saturation region. This region we call it as saturation region. If the point is fixed at near to the saturation region, what happens? We will see. So this is the input signal. So this is the input signal, is one cycle 0 to 2 pi. So this operating point or Q point is fixed to nearer to the saturation region. So there is a current. Current is cut. Positive portion is something clipped. Negative portion is as it is. Whereas in voltage, so this is the IC current waveform. This one is the IC current. Here voltage, VCE voltage. In the form of voltage, here also there is the negative portion. So there is a clip will occur in this, because of if the Q point is placed nearer to the saturation region. So there is a clip or some portion, some information we lost in this graph, because of Q point is fixed at nearer to the saturation region. Okay. So positive peak. So operating point nearer to the region gives the clipping at the positive peak. Positive peak is clipped here. Positive peak is clipped here. Here also positive peak is clipped here. Okay. So this is one case. We will see other case. So in previous, Q point is fixed nearer to the saturation region. In this graph, this Q point is fixed nearer to the cutoff region. This region is called cutoff region. So this is the Q point. Q point is fixed nearer to the cutoff region, whereas in previous, this Q point is fixed to the here nearer to the saturation region. Now this Q point is fixed to the nearer to the cutoff region. What happened? So this is the input signal. So input signal is given. So here a negative peak. So collector current. So amplified collector current is clipped at the negative peak. Here also VCE voltage is also clipped at the negative voltage. So operating point near to the cutoff region gives the clipping at the negative peak. So in both cases, some information we lost. So some portion of wave is clipped. So in previous one, if the operating point or Q point is fixed to nearer to the saturation region, there is a positive portion is clipped, whereas Q point is nearer to the cutoff region, there is the negative portion of the wave is clipped. So this is the disadvantage. So here Here Q point is fixed at the middle of the active region. Q point is fixed. This is the middle of the active region. So we know that flat regions, these flat regions is called as active region. So Q point is always here, middle of the active region or middle of the DC load line. What happened? This is the input signal 0 to pi. So here IC, this one is called IC, collector current. This one is called VCE. This one is called VCE. Here collector current is amplified something. Here voltage signal is also amplified. There is no clipping. So there is no portion is clipped here compared to previous one because of Q point is fixed at the middle of the active region. So the operating point or Q point at the center of active region is most stable. So we are talking about stability concept. How to stabilize the amplifier means we have to put the operating point or Q point at the middle of the active region. Then that amplifier gives the stability. Okay, most suitable or stability. So this is the three cases. If Q point is nearer to saturation region, what happens? Some portion or some information is missing. If Q point is nearer to cutoff region, also some portion of information is missing. So we always desirable or preferable, we want to put the Q point at the middle of the active region, then we will get the amplified signal with stability. Okay. So what do you mean by stabilization? So the maintenance of operating point is stable is known as stabilization. See, the maintenance of operating point. So this is the maintenance of operating point. So based on by varying the VCE, we want to put this IC value at different points in active region only. From this point to this point, we call it as active region. In active region, we will put anywhere. If DC load line is there, we have to put here. So that is called stabilization, the maintenance of operating point. So operating point is nothing but this one, VCE comma IC. Operating point is nothing but, so this is the point, VCE comma IC, we call it as operating point or Q point. There are two factors responsible for shifting the operating point. So generally, two factors are responsible for shifting the operating point or Q point. First one is transistor parameters or temperature dependent. So what are the transistor parameters? So transistor parameters are temperature dependent means one is IC naught, leakage current, current amplification factor beta, and voltage, base emitter voltage. These are all parameters, transistor parameter, which are temperature dependent. When a transistor is replaced by another of same transistor type, there is a widespread in the value of transistor parameters. Even though transistor is replaced with the same type of transistor, there is a values of transistor parameters also change. These parameters also changes. So stabilization of operating point is necessary. We have to stabilize this operating point at a particular location. It is the necessary thing. So these following reasons we can eliminate or reduce. So these are the following reasons. One is temperature dependence of IC, and other one is individual variations, and the third one is thermal runaway. Okay. So what do you mean by temperature dependency of IC? So IC means collector current. It depends on temperature. So as temperature increases, the value of ICE, beta and VBE gets affected. So collector emitter current, that means output side collector current, beta means amplification factor, and VBE means base emitter voltage gets affected. That means increase or decrease based on temperature. So ICB0 gets doubled for every 10 degrees centigrade rise in temperature. If, for example, if temperature is 10, if temperature is suddenly increases to 20 degrees centigrade, then ICB0 gets doubled. So VBE decreases by 2.5 volts millivolts for every 1 degree centigrade rise in temperature. Okay, so that is the temperature parameter, temperature dependence of IC. Now we will see the individual variations. In the individual variations also, if transistor is replaced with another transistor also, these parameters will change beta and VBE. Okay, because if same material also, so these parameters are different, transistor to transistor and model to model. Okay. Third one is thermal runaway. So what do you mean by thermal runaway? So depending upon the construction of a transistor, the collector junction withstand the maximum temperature. Generally, transistor is constructed like this. So collector current can withstand the maximum voltage because collector current is the output side. Okay. The range of temperatures lies between 60 degrees centigrade to 100 degrees centigrade for germanium diode. Similarly, 150 degrees centigrade to 225 degrees centigrade for silicon. So this is the temperature range. So from 60 degrees centigrade to 100 degrees centigrade, this is for germanium diode. 150 degrees centigrade to 225 degrees centigrade, this is for silicon diode. If temperature is increases more than that 100 degrees centigrade or less than 60 degrees centigrade, there is a instability in any amplifier circuit. In militaries also, it's less than 0 degrees centigrade temperature somewhere and greater than 70 degrees centigrade somewhere. So based on temperatures also these variations are differ. So we will choose different amplifier in per military purpose also. Okay. So when the collector current flows in a transistor, it is heated. Okay. When a collector current flows in a transistor, transistor is get heated. So that is, if temperature is increases, what happen? If no stabilization is done, it is the ordinary amplifier. So the collector leakage current is also increases. I am talking about it is an ordinary amplifier. If temperature is increases, collector current increases. If collector current increases, transistor get heated. So if no stabilization is done, so the collector leakage current is also increases. So further, the transistor temperature is also increases. So that is called as thermal runaway. I will repeat. What do you mean by thermal runaway? So in ordinary transistor amplifier, if temperature is increases, output side collector current is also increases. If collector current is increases, transistor get heated. Okay. If transistor get heated means reverse current is also increases. So that is due to thermal runaway. So thermal runaway means one point to other point to other point. That is called runaway. It is a cycle. So when a collector current flows in a transistor, it is heated. That is, if the temperature increases, the collector leakage current is also increases. Okay. So the collector leakage current or the action becomes cumulative here. You can see first temperature increases, IC current increases, then reverse saturation current increases, then transistor get heated, then again reverse saturation heated, transistor get heated. So that is called cumulative process. That the process ultimately damage the transistor or burn the transistor. That is called as thermal runaway. That is called as thermal runaway. Okay. So the following two techniques for stabilization. So these are the disadvantages. So these techniques are used to minimize the above errors like thermal runaway, temperature dependency of IC, and what is the third one? Individual variations. These things can be minimized by using stabilization techniques. So stabilization techniques are two things are there. One is stabilization technique, other one is compensation technique. So first of all, what do you mean by stabilization techniques? Okay. So stabilization technique means we have to stabilize the variation of transistor parameter due to temperature variations. That is called stabilization technique. So we can also define as stabilization techniques consist of biasing circuit which permits variation of base current IB so as to maintain the IC almost constant in spite of variation of IC naught, beta and VBE. So that is called stabilization technique. See, in thermal runaway, if temperature increases, IC increases, IC naught increases. If IC naught increases, transistor get heated. So that is instability process. So to minimize that, whenever base current is also varying, to maintain the IC almost constant in spite of variation of beta, IC naught and VB. So that is called stabilization technique. What do you mean by compensation technique? So compensation technique is a technique temperature sensitive devices such as diodes and thermistors and sensistors are used. Such device produce compensating voltages and current in such a way that operating point is maintained. So compensation, the name suggests some compensation. If temperature increases, IC levels increases, by using some other devices, electronic devices, we can compensate. If temperature increases, we have to reduce the heat by using some transistor or diode or some other thermistor, some other devices. That is called compensation techniques. Okay. So there is a two different stabilization technique is nothing but we have to maintain the IC at constant. Here also by using compensation techniques, we have to maintain the IC. Here also same purpose. IC is constant at output side. So stability factor. There are three variables which are temperature dependent. We can define three stability factors. So three variables means three stability factor. We will define one by one like S1, S. First one is S, S dash, S double dash. So S for first parameter, second parameter and third parameter. We will see one by one. See, yes, here the stability factor S is defined as the rate of change of collector current IC with respect to the reverse saturation current IC naught, keeping beta and VBE constant. See, the rate of change of collector current IC with respect to the reverse saturation current IC naught. So at keeping beta and VB are constant. Here three parameters. One is IC naught. Second one is beta. Third one is VB. Three parameters means three stabilization factors. So which is equivalent to change in IC by change in I naught at constant beta comma VB. Second stabilization factor, that is for second variable. The stabilization factor S dash is defined as the rate of change of IC with respect to VBE. So here change in IC by change in VBE. Here beta comma IC naught are constant. In the previous one, beta comma VBE are constant. IC naught is the change in IC naught. So this is S dash. Next one is S double dash. The stability factor S double dash is defined as the rate of change of IC with respect to the beta. Beta means amplification factor. Beta keeping IC naught and VB are constant. So generally stability factor should perfectly zero to keep the operating point is stable. Practically stability factor should have the value as minimum as possible. So we have to maintain the stability value or stability factor less than 1. If 0 means perfect stability, means if stability factor S is equal to 0 means that operating point at the middle of the DC load line, so which is amplify entire signal. That is the meaning. Okay, stability factor is always less than 1. Okay, if stability factor is nearer to the 1 means there is no stability. Means operating point is near to saturation region or near to cutoff region. So it gives the unfaithful amplification. So we always preferable thing is stability factor is very nearer to 0. So derivation of stability factor we will see. So we know that in emitter configuration, so this is the collector current is equal to beta IB plus IC UO. So IC is equal to beta IB into 1 plus beta into IC naught. So we know that this equation. So differentiating equation 1 with respect to IC. IC means collector current. We are always differentiating with respect to IC because collector current is the output side. So keeping beta is constant, we get. So IC with respect to IC means differentiation of IC with respect to IC means 1. So this one is 1 is equal to beta into. So differentiation with respect to IC means dou IB by dou IC. With respect to IC means dou IB by dou IC. Beta is constant here. Plus same 1 plus beta. Same thing here 1 plus beta into dou IC naught by with respect to dou IC. Dou IC naught by dou IC. So we will keep this side 1 minus beta into dou IB by dou IC is equal to 1 plus beta into dou IC naught by IC. Okay. So from above equation we will get dou IC by dou IC naught is equal to 1 plus beta by 1 minus beta into dou IB by dou IC. See, so this term, whole term come to this side means 1 plus beta by this whole term and this term is shifted to here, means it is numerator is changed to denominator, denominator is changed to numerator. Okay, so dou IC by dou IC naught is equal to 1 plus beta by 1 minus beta into dou IB by dou IC. So S is equal to 1 plus beta by 1 minus beta into dou IB by dou IC. So this is the stability factor. This is the stability factor. We have to calculate for every amplifier stability factor, whether it is 0 or less than 1, or we will find what value it have. If stability value is less than 1, means it is more stable. If nearer to 1, means it is unstable. So to obtain stability factor S dash and stability factor S double dash, to get S dash, replace IB value here, IB value, replace IB value in terms of VBE in standard equation of IC. Similarly, to get S double dash, differentiate the equation of IC with respect to beta after replacing IB in terms of VB. So you will come to know when we are doing problems how to differentiate S dash to S double dash, how to replace IB in terms of VBE. We will come to know while doing problems. Okay. So this is the stabilization techniques. So let us briefly recapitulate or what I discussed today's session. So in this session, I talked about stabilization. So what do you mean by stabilization? So stabilization means if Q point is nearer to saturation region or it nearer to cutoff region, there is a instability in amplifier. So we always fixed the Q point at the middle of the DC load line in the active region. So that is called Q point or quiescent point or operating point. So this stability depends on temperature, individual variations, and thermal runaway. So what do you mean by temperature? If temperature increases, so ICE value at the output side increases. So if ICE increases, means VBE voltage is increases. If VBE voltage is increases, means amplification factor is also increases. If three parameters increases, means IC current is increases. So transistor get heated. So that is one reason. Other reason is individual variations. Or individual variations means if we replace transistor to new transistor with same type, at that time also some variations will occur. Next one is thermal runaway. So in thermal runaway means whenever varying VBE, whenever varying IB current, base current, IC also increases and VC also increases. We have to fix them. An ordinary diode, ordinary transistor. So if IC is increases, transistor temperature is also increases, IC increases. If IC increases, VC is increases. If VC increases, means transistor get heated. If heated means again because of heat, collector current is increases. So this is the cumulative process. So this cumulative process, because of cumulative process, transistor may burn out at some point of time. So this thing can be minimized or reduced this problem by using stabilization techniques. So stabilization techniques are two types. One is stabilization technique, other one is compensation technique. So stabilization techniques means we can stabilize the amplifier even temperature variations like VBE, beta and IC. Even though they are varying, we can put amplifier in a stable state. That is called stabilization technique. So what do you mean by compensation technique? So compensation technique means if transistor collector current is increases, how much collector current is increases, that current can be decreased by using some compensation devices like diode, thermistor and transistor. That is called compensation techniques. We will see later. So today stabilization techniques we've seen based on three parameters. One is VBE, beta, IC naught. S is equal to change in IC by change in IC naught. That is called stabilization factor S with constant of beta comma VBE. So second stabilization factor S double S dash denoted by change in IC by change in VBE at constant of beta comma IC naught. So third stabilization factor S double dash is equal to change in IC by change in beta at constant of VBE comma IC naught. So these are the three different stabilization factor. So yes, so final formula, yes, stability factor is equal to 1 plus beta by 1 minus beta, 1 plus beta by 1 minus beta into dou IB by dou IC. 1 plus beta by 1 minus beta into dou IB by dou IC. So stability factor always we have to maintain less than 0. So if 0 means it is good, greater than nearer to 1 means it is bad. Bad means there is no stability, means there is unfaithful amplification will occur at the output side. So we have always maintained the stability factor, it is nearer to 0, so that Q point will be uh, occur in the middle of the DC load line of of active region. So this is called stabilization, transistor stabilization. Okay, thank you.